Hello, welcome to everyone. In the previous lecture, we studied about self-induction. Okay, the outline of the today's lecture is yeah. Today in this lecture, we study the self-inductance of a long solenoid and mutual induction of two given coils. Okay, we are going to cover these three topics in this lecture. Okay, first of all, let us go for the self-inductance of the solenoid. Self-inductance of the solenoid. Self-inductance of the solenoid. You are trying to calculate L of the given solenoid. You know what is solenoid? It's a coil, long coil. Okay. Yeah. Always we take an ideal solenoid. So our discussion will be simple. So in this case, the magnetic field inside of that solenoid is known to us. We are already derived the expression for that. Okay, you can see on the slide the solenoid of length small l. Okay, so let us suppose that there are n, capital N turns. Okay, in that solenoid, let us consider a solenoid of length L and number of turns n. Okay, then what happens? Now the number of turns per unit length. We are going to define one more quantity, and this becomes now n by L. N by L. Okay, now the magnetic field. The magnetic field inside the solenoid B is equal to, we are already derived this by using the Ampere's law. You know that this is B is equal to mu naught and I. What's I? I is a current flowing through that solenoid. That solenoid. Okay. Now let us go for the basic definition of the magnetic flux. Yeah. Using the definition of magnetic flux, the flux phi is equal to, yeah, B ds, B integral ds means simply I am writing B integral ds means A. Okay, let us suppose that A is the area of each coil. Area of each coil. Okay. If you have n coils, because we are having capital N turns, for capital N turns, let us write this as big phi. Okay. Phi is equal to n times of this small phi. This is equal to NBA. NBA. Okay. So the total flux is equal to NBA. Okay. Or you write this as NAB. Okay. Right. Now you have the total flux within the solenoid and the magnetic field. Okay. These two things are interrelated. Interrelated. Now, say this is equation number 1. Okay. Now, this is earlier equation. Now, say this is 1. Say this is 2. Okay. Yeah. Now, from 1 and 2, you use b from 1. You substitute b from 1 into equation number 2. Okay, you write b here. So from equations 1 and 2, from equations 1 and 2, we have C, B, or 5. We are writing B here now. Now what happens to your phi n? What is B from this equation? Mu naught n I into A. Okay, I'm not changing that. Okay. Now we utilize the first equation in the second equation. Right? Now you just write for n, but your n is equal to n by L. Huh? Okay, then what? Then simply write your n is equal to n into L, small n into small l. So you write this n is equal to nl here. Therefore, what happens to your phi? You write in the place of n, nl. nl mu naught nia. This is equal to how much? Yeah, n square, n into n square mu naught I, okay, into L, n square mu naught I into L. Yeah. Next, again you are having here A also, no? Okay. A also. Okay. So, what you have here? N square mu naught ILA. ILA or AL. Okay. Right. But what is this? Length into area is a volume. So you have phi is equal to, otherwise I will write here. Therefore, phi is equal to, okay, with phi is equal to n square mu naught I. What is this AL or LA? Volume. Okay, say this is some equation number 3. Okay, now you want self-induction. There is a relation between phi and L. I am using that relation to get L from phi. Using phi is equal to Li. Just now we studied this equation. What you have now? When you write for phi Li here, Li is equal to n square mu I V. I cancel. Therefore, you have self-induction or inductance of the solenoid as n square n square mu naught V. So what is the expression for the self-inductance of the solenoid? Yeah. So what is L here? N square mu naught V. Now, yeah, what is L here? N square mu naught V. You see the dependence of L. You observe here on what factors L is depending. Is there I in this expression? In the RHS? No. That's why self-inductance or coefficient of self-inductance or inductance does not depends on current flowing through the coil, in this case solenoid. But it is depending on N and V. These are all intricately related to the structure of the given solenoid. Okay, defining these things will describe the solenoid only, irrespective of the current. So, Self-inductance or inductance of any object, any coil depends on the shape and size of the coil. How many turns are there? What is the area? What is the length of that coil? Okay, it depends on these things. Okay, length and shape of the coil or the geometry of the coil. Okay, right. So I is independent of the current. You have to note from this. This is a constant for one coil with particular configuration or one coil with particular geometry. If you go for another coil, its geometry changes. That's why you have another induction value for that coil. Okay, this you have to note. Here, what is mu naught? Where you are placing your coil. Okay, it also influences this by inductance. Okay, in the free space you are placing the solenoid, then you have this much L. If you are placing in a medium, then you have mu like that. Okay, right. Yeah. So one important thing you have to note is it is a constant for particular coil. It does not depends on the oil. Okay, now this point is clarified. Okay, even though we derived this for the solenoid, it applies everywhere. That means the statement which I just uh, talked about is applicable everywhere. That means if you derive the expression for the inductance of any coil of any shape, that does not depends on the current flowing through that coil. This statement applies everywhere. That means that what is that statement? Inductance is independent of the current. That you have to know. This is just one example for us. Okay, solenoid. Right. Yeah. Now let us see what is mutual induction. Yeah. To say this, let us consider a current carrying coil. Okay, you can see this on the slide as well. Okay. Yeah. Here we have to assume one more coil very near to that first coil. Okay. Then there will be a magnetic coupling between these two coils. This can be explained by using the concept of mutual induction. Okay, mutual induction. Yeah, we already know that current passing through a coil induces some self-induction in itself, generates some self-induction in itself. Okay. Yeah. Now we have one more coil in addition to the first current carrying coil. Okay. Now, due to the current passing through the first coil, there is some induced magnetic field around that wire. That means the flux is passing through that loop or coil. Okay. See, we are just placing the second coil very near to that coil. The flux which is bounded by the current carrying coil also bounded by the second coil or loop. Okay. Now, as the changes in the flux bounded by the first current carrying wire induces some induction, self-induction, generates some self-induction in itself, and the same flux is bounded by the second coil. In case of the second coil also, this varying flux is able to create some EMF. We call that as a mutually induced EMF. Okay, we call that as mutual induction. Okay, we're able to see the EMF in the second coil due to the mutual induction between the two coils. Okay, this is the phenomena of mutual induction. Okay, here we have to note difference between what is the difference between self-induction and mutual induction. Okay, Yeah, we have to note the difference between self-induction and mutual induction. Okay, see, in case of self-induction, we are having only one coil. In that coil, we are having the current. Okay, yeah, due to that varying current, there is some magnetic field, varying magnetic field around that wire. That means the flux of that magnetic field is changing. Okay, this is what again generating some EMF in the first coil. We call this as a self-induction. We call this as a self-induction. Okay, then what is mutual induction? In addition to this coil, we have to take some second coil, another coil. Okay, since we are placing that coil very near to the first coil, as there is a variable flux bounded by the first coil, the same magnetic flux is also bounded by the second coil. Since this flux is varying, this is able to generate some induced EMF in the second coil as well. Second coil as well. Okay, we call this phenomena as mutual induction. So, how to define the mutual induction? You can see that on the slide as well. Mutual induction is the inducing of an EMF in a secondary coil, that means second coil, due to the variations of the current in the primary coil or the first coil. Why do we have some induced EMF in the second coil? Due to the variations of current in the first coil. Okay, due to the variations of the current in the first coil. If we are talking about the induced EMF in the first coil due to the variation of current in the first coil itself, then we call that phenomena as a self-induction. Okay, this is what the difference between self-induction and mutual induction. In case of self-induction, you have only one coil. Okay, in case of mutual induction, you must invariably have to choose two coils. Okay, right. This is about the mutual induction. Yeah, now you can see the slide. Yeah, we are connecting a coil to the battery, and we are connecting another coil to the ammeter. Okay, here there is a core between these two coils. Of course, no, it is not always necessary to keep the common core between these two coils. Okay, now whenever you just close the switch and open the switch, then what happens? Variable current flows through the coil. Variable current flows through the first coil. Okay. Due to this variable coil, you have variable magnetic field within the core. Within the core. Okay. Since this core is shared by the secondary coil, second coil, so this varying flux is also bounded by the second coil. Since the second coil is within the variable magnetic field, our second coil is bounded by the variable magnetic field. Due to this varying magnetic field, you have an induced EMF in the second coil. So, in this way, due to the variations of current in the first coil, okay, there is some induced EMF in the second coil. Okay, this phenomena is called as a mutual induction. Mutual induction. Okay, this is a mutual induction between these two coils, right? Due to this mutual induction, you have some non-zero current in the ammeter connected to the second coil. Ammeter connected to the second coil. Okay, right. Now, let us try to discuss in a more detailed manner about this mutual induction. Okay, here the discussion is very much similar to that of the self-induction. Okay, there we define inductance. Here we define mutual inductance in case of two coils. Okay, right. Here also we are having some flux. Okay, that flux is linked with the first and second coils as well. Okay, whatever the flux we are taking here is the flux linked with the second coil. Flux linked with the second coil. Okay, this flux will be proportional to the current flowing through which coil? First coil. That is what the difference between the discussion of self-induction and mutual induction. You can see this on the slide. Okay, here phi flux linked with the second coil is proportional to the current passing through the first coil. Okay, yeah, mutual induction. So in this, flux is proportional to the current. Means this is the flux linked with the secondary coil. This is the current flowing through the primary coil or the first coil. Okay. So whenever you remove this proportionality symbol, you have to introduce a proportionality constant. Let us call that as m. So now we have phi is equal to mi. In case of self-induction, you have phi is equal to Li, okay, where L is the coefficient of self-induction or simply inductance. Then what is M here? Where M is a mutual inductance or the coefficient of mutual induction. Where M is a constant called mutual induction. Mutual induction is a constant. You see, this is a constant for a given pair of coils. Okay, it does not depend on I. It does not depend on I. This is very similar to the inductance of a coil. Okay, in the self-induction. Okay, so mutual induction is a constant. It does not depend on the current flowing through the coils. Okay, it is only depending on the shape and the size of the given pair of coils that we have to know. Okay, but it is independent of the current flowing through any one of those two coils. Okay, right. Then you may ask, what may be the units of this mutual induction? It is also an induction. That's why we have the same units for the mutual induction as well. What are those units? Henry H. Henry H. So the units of mutual induction also Henry. Right. Now let us try to define this Henry here. See here, M is equal to, by using this relation, you have M is equal to phi by I. So now we may define this mutual induction or the units of mutual induction. Whenever you make this I is equal to 1 amp and whenever you make this phi 1 Weber, then okay, we will write here phi so by using this relation you have M is equal to phi by I. Whenever you make I is equal to 1 amp, phi is equal to 1 Weber, then you have M is equal to 1 Henry. Then you have M is equal to 1 Henry. Okay, here this is the current in the primary coil. Okay, this is the flux in the secondary coil. Secondary coil. Okay, then you have the mutual induction between those two coils as 1 Henry. Okay, whenever 1 ampere current flowing through the primary coil is able to induce 1 Weber flux in the secondary coil, then we call that the mutual induction between the two coils as 1 Henry. Okay, in this way, we have to define here the Henry. Okay, Yeah, similar to the self-induction, let us try to give the EMF of the mutual induction. Okay. Here, for this purpose, we use Faraday's law as in the case of self-induction. Okay. Yeah. Let us call this induced EMF. Okay. Here we have induced EMF in the secondary coil. Okay. This is the EMF of the mutual induction. According to the Faraday's law, any induced EMF can be written as a negative rate of change of magnetic flux. Okay, just now we wrote phi as m of I. Okay, so therefore EMF of mutual induction is equal to minus d by dt of mi. This is equal to minus m di by dt. So the EMF of mutual induction is given by minus mdi by dt. Okay, in case of self-induction, we have L here. We have L here. Here, this rate of change of current is in the primary coil. Okay, this is a induced EMF in the secondary coil. So the direction of the induced EMF in the second coil is such that it opposes the change in current in the first coil. Change in current in the first coil. Okay, in this way we have to interpret this equation. Okay. Here by using this equation also we may define M. Why? Because you have M is equal to how much you have EM by, okay, EM by di by dt. Okay. Now if you just to take the magnitude of this EM by di by dt. So how to define this M? Then by using this formula EM. So by using this relation you have M is equal to EM by di by dt. Just let us take the magnitude of this. Yeah. Whenever you make this unit 1 ampere per second. Next, whenever you make this unit, then your EMF is nothing but the mutual induction. Whenever you make it 1, then what happens? Mutual induction becomes just the induced EMF. Induced EMF. This is the rate of change of current in first coil. This is the induced EMF in the second coil. Okay, whenever you make the rate of change of current in the first coil as a unit quantity, then the EMF induced in secondary coil is known as the mutual induction. Is known as the mutual induction of the two coils. Okay, right. In this way also we can define mutual induction between the two coils. Okay. After studying about the mutual induction, now we will go for the mutual induction of two coils. Mutual induction of two coils. Mutual induction of two coils. Okay. Yeah, let us take two coils. Okay. With the air core. Okay. You can see this on the slide as well. Okay. Now you imagine that you are taking a pipe and you are having two turns, two coils on that pipe. Okay. Or we may call this as a air cooled solenoid with two coils. Okay. right? One coil is see like this. Okay, we are also having another coil here. Okay, there are two coils. Say this as a coil 1, say this as coil 2, okay, or coil A or coil B. Okay, suppose that you are allowing the current to flow through this primary coil, say that current I. Okay, okay, suppose that I current is flowing through this first coil, okay, or coil A. There is another coil B which is just above huh, that primary coil, coil A. Okay, both are like uniaxial coils. Okay, now this is coil A. Okay, on this coil A, okay, you have coil B as well, coil B as well, right? Now, due to the change in the current flowing through the current coil I, you have some changing magnetic field. Okay, changing magnetic field around this coil A. Because you are placing coil B just above this coil A, this flux will also be linked with the coil B. So this changing magnetic flux linked with coil B induces some EMF in coil B. Okay, this is what mutual induction. Now we want to find the magnitude of mutual induction between these two coils. Okay, right. You can see this on the slide as well. Yeah, let us suppose that there are n turns in the coil A and 1 turns in coil A. Let there are n1 turns in coil A and n2 turns in coil B. Okay, let us suppose that there are n1 turns in the coil A and n2 turns in the coil B. Okay, right. Now we know that coil A is nothing but a solenoid. We know the magnetic field inside this solenoid. Inside this solenoid, what is that magnetic field of coil A is how much? Okay, I'm writing here B1 because it is the A coil or the first coil. Let us write this as B1. Okay, B means magnetic induction vector. Okay, B1 of coil 1 is mu naught N1I. Okay, because we are supposing that I current is flowing through this wire and this coil is having N1 turns. Okay, we are directly taking away the formula of the magnetic field of a solenoid, which we already derived in the previous unit. Right. B1 is equal to mu naught N I. Okay. Now, what is the flux corresponding to this field? What is the corresponding flux? Corresponding flux phi is equal to, here we know the definition of flux phi is equal to integral VDS. Integral ds is again total area. Okay, then we have BA. Let us suppose that A is a total area. A is a total area. Now, this flux is linked with the second coil, B coil. So what will be that total flux linked with the second coil? Total. This is the flux of the first coil. Total flux linked with the second coil is, say this as some capital phi, okay, is equal to uh, sorry, here this is the flux corresponding to each turn of the first coil. Now let us suppose that there are n2 turns in the second coil, capital N2. Okay, then what will be the total flux of the second coil? What will be the total flux linked with the second coil? When we consider all the turns of the second coil, that will be N2. This is B1, huh? Okay. B1, B1A, N2, B1A. Okay, right. We can see this on the slide as well. Okay, now let us substitute for B1 here. N2 mu naught N1 I into A. Okay. Now let us consider the number of turns per unit length of coil 2. We are already assumed these quantities to be N1 and N2 for the first and second coils, small n1 and small n2. Okay. So now you have phi is equal to this thing. But n2, small n2 is equal to how much? Capital N2 by L, if L is the length of the secondary coil, if L is the length of second coil. So, but small n2 is equal to this thing, or capital N2 is equal to small n2 into L. Okay, therefore you have total flux now as, I will write here, total flux here, this is equal to, what is this N2 now? Small n2 L, small n2 L into mu naught n1I A. Okay, now, okay, this is equal to mu naught n1 n2 I A L A, L A, or A into L. Okay, what is this? This is the area, this is length. Area into length is volume. That's why we write this as mu naught n1 n2 IV phi. So what is the flux linked with the second coil? Mu naught n1 n2 IV. But we are already having one formula for the flux linked with the second coil. Okay, in which we have induction due to mutual induction between, okay, two coils. Since this phi is equal to mi, just now we wrote for phi as mi. This is the current in the first coil, this is the flux linked with the second coil, this is the mutual induction. Okay, since phi is equal to mi, you have mi is equal to mu naught n1 n2 iv. Okay, so now I cancel, you have, therefore m is equal to mu naught n1 n2 v. So what is the expression for mutual induction? This expression will give you the magnitude of mutual induction between the two coils, 1 and 2, or A and B. Is it the function of I? No, there is no I. So mutual induction between two coils does not depend on the current flowing through any one of those two coils. It just depends upon the shape and size, as we already noted. See, it depends on N1, it depends on N2, it depends on the volume of each coil. Okay, so this M is independent of I, as in the case of L, that means ordinary induction, self induction. Okay, so this is confirming us that the mutual induction between any two coils does not depend on current. Okay, it not only applies to our two coils in this solenoid with two turns, it is applicable everywhere. Okay, mutual induction that may be there anywhere, but that does not depend on the pair of coils there. That means on the current in any one of the pair of coils available there. It only depends on the number of turns per unit length in each coil and the volume. Okay, apart from that, you will see here the mu naught also. That means medium, where you are placing these two coils. Okay, what is the core material? Here we considered free space, that's why we have mu naught. Okay, so it depends on the medium also, or the core material also, but not on the current. See, you may change any magnitude of current. Okay, you may introduce any change in the current in any one of the two coils, but it does not mm, influence the magnetic induction between those two coils. Yeah, just allowing small current or the large current does not change the character of that coil. Okay, mutual induction character of those two coils available. This we have to note. So it is a constant. It is independent of current. It only depends on the medium as well as the individual characteristics or the geometries of the given two coils. So we have to note here that there are many similarities between self-induction and mutual induction. There are so many similarities between self-induction and mutual induction. Okay, there, in case of self-induction, the self-induction does not depends on the current flowing through that coil. Here, in case of mutual induction, instead of one coil, you have two coils. Here also, this mutual induction does not depend on the current flowing through any one of those two coils. Okay. In case of ordinary induction or self-induction, it depends on the geometry of that one coil. But in case of mutual induction, it is the combined characteristic of two coils. That's why it depends upon the shape and size of the two coils. That's why you have N1 and N2 here. Okay. Yeah, this is what the similarities and the differences between the self-induction and mutual induction. Self-induction is nothing but you have phi is equal to Li. What is another equation? What is another equation? S is equal to minus L di by dt. Es is equal to minus L di by dt. What is another equation? Es is equal to minus L di by dt. Okay, L is equal to, here also you have EMF by di by dt, magnitude of L. So this self-induction can be defined as the EMF induced in that coil due to the unit rate of change of current in that coil. Okay. Similarly, in case of mutual induction, here you have M is equal to E foot M di by dt. In case of otherwise, I will write here M is equal to Em by di by dt. Why? Because Em is equal to, you have minus M di by dt. That's why M is equal to this much. Em by di by dt. So what is mutual induction now? It is the EMF. It is the EMF for the unit rate of change of current in the first coil. First coil. Okay. In case of ordinary induction, what happens? Induction is nothing but the EMF induced for unit rate of change of current in that coil itself. In that coil itself. Okay. Here, this EMF is related to the second coil. This rate of current is related to the first coil. That is what the difference between self-induction and mutual induction. Self-induction and mutual induction. But the units for these two physical quantities are same. Mutual induction and self-induction are having, or the induction are having the same units, SI units, Henry. Henry. Okay. All right. So you have to note these similarities and differences between the self-induction and mutual induction. Okay, yeah, let us stop with this. Thank you.